Shalom lekulam. Thanks for inviting me. I will speak today about actually there will be interleaved three different topics. And one is introductory, one is about really the machine learning at scale, and the very last part is for people who do machine learning on a daily basis. It's going to be a teaser. And if time won't permit me, I will skip the last part. And please free to ask very brief questions. I will try to answer questions at large at the end of the talk. Okay, so what I'm going to talk today is about, I'm part of the Google Brain, so this is mostly not my work. It's a work of a team. It's a work of a team of about 400 people. Most of them reside in Mountain View in California, but we have other branches, including people in Israel. So let me start with an example. Suppose someone from Mars comes to sort of drops into Tel Aviv and would like to eat something. He's hungry, and we would like to teach the person what should he eat and what should not, what he should avoid, right? So in machine learning, we simply give examples of good foods, healthy foods. Wait a minute, wait. No, that's the right place, okay. And not so good food, right? So we call these positive examples and negative examples. And in the past, we didn't have that many examples, but these days, right? So we want to learn how to classify them. These days, what we have is often forms, and what you see here is this is a form of robotics arms from Google X, and let me see if it will work. What you see here, they are trying to learn how to grasp elements. Okay, this video is actually available on YouTube if you'd like to find it, and the robots themselves generates many negative examples. A negative example when they try to grab something and they don't succeed. And positive example when they grasp something and they're able to grasp it and lift it. So naturally there are many negative examples, failures, and a few positive examples. But these positive examples would suffice to actually teach a robot how to grasp an arm. To grasp an element. Okay? So these robots are not just robotics arms, they have cameras on them, and they would like to, what the cameras do, they actually learn whether the orientation, for instance, is good or bad, whether the grasp is correct or not. So these are neural cameras or deep architectures cameras, which simply when you show it an element, in the case of food, it will say positive or negative, good or bad. Okay? Now, what are these neural networks? So this is, again, just really for a brief introduction. Neural networks really stem from the notion of neurons in our brains, in the brains of mammals in general. A real neuron is dendrites, which collect information from neighboring neurons. And let me just increase this. And there is a cell body. The cell body integrates the information that comes from the dendrites, and then it outputs something. And the flow information is from the dendrites to the body to the output. And this is, to a large extent, the structure of an artificial neuron. An artificial neuron, is basically inputs in green. Okay, given the inputs, each input is multiplied by a unique weight or non-unique weight, and then there is a function that takes the inputs, sum them, and performs some non-linearity, and that's the output. In pictures, suppose the inputs are these bars. The value of the input is the width of the bar. Then the weights are the perpendicular bars. And then we take a product. So the product is going to be the area. Then we sum them. And then we perform this nonlinearity. And this nonlinearity is essential. Why is it essential? Because it lets us actually build a layer on top of a layer. So here's an example of a two-layer neural network. And what you're going to see is the flow of information from the input to the output. Now, without these neurons in the middle, this two-layer network would have been just equivalent to just a single-layer network. So these nonlinearities are essential in order to build deep architectures. And we can generalize it to more than one layer. Okay. So here's an example of four-layer neural network. And in practice, in the past, we saw, we were working on networks with 7, 10 layers. Today, people often build networks with hundreds of layers. Okay, so what is learning then? So suppose we got some input and we propagated to the output, and the output is these 4 neurons, 4 values at the top, and the color designates the value. So in order to do learning, we need this, supervisor. The person or the environment that will give us this feedback. And the feedback is typically different than the actual prediction. So what you see here is 4 different colors, and there is discrepancy. There is discrepancy between the prediction, our prediction on the left, and the actual feedback on the right. Okay? So we call this divergence or discrepancy. And it comes from a critic. And I call the critic Donald, and it's not what you think. At least in the US, people actually started laughing. Given the difference, there is this error vector. And this error vector is what we use for learning. Okay. So how does learning proceed? And this is, one of the 2 mathematical slides that I have. So given the output of a neuron, we get the error from the critic, either directly from the critic or going down. In a second, I'll show you. And then it's called after Donald Hebb that said neurons that fire together wire together, meaning that if the target is positive, then the output of the neuron should be positive. If the target is negative, the output of the neuron should be negative. Okay? And this is how we update it. So a neural network is not just an architecture. So I showed you this 4-layer architecture, but what is more equally important are the weights. And the same neural network with different weights can actually have completely different characteristics, can perform completely differently. So the goal of learning is to adjust the weights so that it will match the target outputs. It will match what the teacher tells us, the supervision. Okay, so how does this update looks like? So look at one edge, one connection from one neuron to another. We call this weight the weight from R to S. R is a neuron and S is a neuron. So in order to learn, we take the output here of the previous layer, the supervision from the previous layer, top layer. We multiply them together. And then we multiply it by a scalar, A. This A, I call it in Hebrew kotzban alimud, because I didn't make a mistake here. It's kotz batachat. It's a scalar. In English, we call it learning rate, that helps us adjust our rate. So high value, large value means high rate. Small value is a slow rate. And if sometimes we need to learn fast and sometimes we need to learn slow. So one particular architecture that is relevant to our neurocamera is called convolutional networks. In convolutional networks, instead of having general neurons, we have what we call locally tuned neurons. These are, for instance, neurons that look at part of the image, okay? And then they propagate their value upwards. Okay, so a neurocamera can tell us whether the input is positive or negative, or a steak, or organic oatmeal. Okay. So the first step of training and also predicting a neural network is what we call the forward pass. This is when we take the input and we propagate it through the network. Every propagation amounts to taking the previous output multiplying it by its value, summation, and then nonlinearity. Then we get the supervision in training, only during training time, and based on the supervision, we propagate the error down and adjust the weights. So this propagation doesn't just propagate the error downwards, but also adjust the weights. Okay? And by now you can go and actually say that you're experts in deep learning, because this is really what deep learning is all about. It's really just about what we call gradient-based learning. Pardon? Why am I laughing? Let's take it offline. Okay, but in practice, it's not just this previous slide, right? There is a lot that lies underneath. There are algorithms and data sets and massive computation and more advanced algorithms that sometimes really cut the amount of training. What I'm going to talk now, after this introduction, is actually a little bit of what's going on inside Google. And let's not forget the supervision, because it's important for learning. So now I'm going to tell you about a problem. So let's see what problem it is. We have the input. It's a very large-scale 3D imaging problem. The acquisition, though, it's two-dimensional images. Camera in, say, on your dashboard, for instance. And there is complex connectivity between parts, and it changes with time. And it's not a self-driving car. The problem is not a self-driving car. So what problem is it? And I tell you, it's actually much bigger than a self-driving car. So this problem is called the connectomics. It started by a colleague of mine, Sebastian Sung from Princeton, and we have a project called the Neuromancer project, led by Tom Dean and Viren Jain. Viren was a student of Sebastian. And the goal is to take a slice of a brain. There's no technology that slices it into thin slices, like salami, like these thin cheese slices, and to try to reconstruct the connectivity and functionality of neurons in a brain. Okay? So they don't work with human brain. They work with songbirds, and they take their brain and they pass it through a high-resolution microscope, slices of these. So here's one slice. This is how it looks like. And what you see is a very complex structure. What are these dark dots? Any guess? Pardon? No. These are actually very important, but they don't do any computation. Blood vessels. So we get, one piece is of this size, 10,000 by 10,000 by, and we have many pieces like this. And the goal is to take all these pieces, this cube of thin slices, and reconstruct the image, actually the connectivity. So here's actually an example. This is done at Google in the Neuromancer team of part of the reconstruction. It's an algorithm called watersheding. I'm not going to get into it. But what you see here, this is an algorithm that traces based on a lot of, based on multiple deep networks that do the image processing. It traces the connectivity. And you see here just a movie, and you would think, oh, this is real time. No, this is actually a few days of computation. Right? So what you see here is basically just one dendrite, okay? But because we can do this in parallel on many computers, the fact that it takes a few days, it's still a few days to do the entire cube of birdsong. So what you see here is the result. It's color-coded because it's not only the connectivity, but it's actually trying to identify boundaries, which neuron is which. So the fact that there are different colors designate that, this is the dendrite of one neuron connected to the axon of a different neuron. It's really like the neural nets, the artificial neural nets that I've described. And this is actually a connectivity map. Now, this is a tiny piece of a songbird. The goal is eventually to do it with humans. Now, how do we do all of this? So at the heart of the computation these days, at least at Google, lies what is called the Tensor Processing Unit, TPU. This is TPU version 2, and working on TPU version 2 is not a sheer joy, but it is actually I can work on. I can use it. The version 1 was something that's really for the experts. It's Google designed. It's sort of designed for neural network training and prediction. It's not necessarily a general purpose unit. It can do large numerical linear algebra. This is the amount of computation of a single board, and it's humongous, right? But it's not just the fact that we have a single board. They are designed to be connected together with very fast memory connection. In fact, when we connect only 8 of them, they can talk to each other through their memory. So TPU1 can write into the memory of TPU2. So when you connect them together, we get a pod. One column is a pod. This is 64 TPUs. This is the amount of computation. And if we view them as one monolithic computing unit, it has 4 terabytes of memory. And this way, we can actually perform tasks like serve queries, right? So this is just a small sort of look through a part of a data center that has TPUs. You may notice the woman at the back. She's actually a technician who rides a scooter in order to get to one part of the data center to another. Now, these TPUs are no longer just research devices. Every search query that you issue, a TPU is involved. In fact, we have now deep architectures, deep learning technology in search. Google Translate is fully neural networks. We actually ditched the old, and WaveNet, speech synthesis is done using TPUs. Okay, questions so far? How much time do I have? 10 minutes, okay. Let me stop here before I go to and talk about more technical stuff, and I'd be happy to take questions now if you have any. All right. Okay, so I spoke about the real basics. I spoke about applications with just a hint of them. I'm going to get back to applications at the end, but now I'm going to talk a little bit to the people who do machine learning or numerical analysis on a daily basis or a semi-daily basis. So let me go back to this pesky thing called learning rate. And this is now a little bit of mathematics. So I gave you this sort of Hebbian rule, but in practice, it's not really a Hebbian rule. The way we learn is called gradient-based learning, which means the following. This is in vector form. Given a set of weights, W, so think of W as a vector, the way we do learning, we take W in order to improve, and we compute something called the gradient. There is a loss function that is associated, I call it the divergence or the discrepancy. The loss function is associated with the difference between my prediction, the network's prediction, and the supervisor feedback. And the way we do we learn, we take the difference, this difference, which we call the gradient, and we multiply it by a scalar A. This is the learning rate, and we subtract it from the current weights. And we get one more example, we need to do again this iteration, and another example, and we do these iterations. Okay? So in a picture, think of the gradient, and this is just a simplification. Forget for a second about the network structure. Think of the gradient as a vector. Then we multiply it by just one number, a scalar A, and then we take the weight vector, we subtract from it the G times A. So G is what is the gradient of the error, and we write it into W. Okay? So this is really the essence, and again, given the slide on forward inference and backpropagation, the previous slide and this slide would make you into data scientists, right? This is really what is going on in most of the learning procedures for neural networks. But the problem is that this learning rate its initial value is very important. If you set the learning rate initially to be very high, you might think, oh, I'm going to learn fast. But what you do is actually going to randomly walk rather than learning. If you set it to be too small, then you won't make any progress. And in fact, you may get stuck in a place which doesn't have any good prediction capabilities. We need to decrease it with time. This is both empirically and from a theoretical point of view. It's clear that this learning rate needs to be decreased, but the actual way to decrease it is really problematic. It takes a lot of human effort, someone in the loop, in very large applications. Moreover, this gradient-based learning is oblivious. It's not aware of the actual network architecture. It doesn't take into account the dynamic range of the gradient components. Why do we have different dynamic ranges? Think of an image. So the sky is typically blue. The bottom is an image of scenes. The bottom is typically brown, and we can take that into account when we do learning in terms of the actual values that we get. It also doesn't take correlation between gradient components. What do I mean by this? If we're looking at the sky and this pixel is blue, the pixel next to it is likely to be blue as well. We might want to take that into account. So the way to do it is to actually wipe out this scalar and introduce a whole matrix. So recall your linear algebra, or just forgive me for asking you to recall this linear algebra. What we do, we take G and we multiply it instead by a scalar. We multiply it by a matrix H, which takes into account the gradient correlations. And then we do, recall that matrix times a vector gives me a vector. So now we get, again, the difference of two vectors. Okay. And, and we write it into my vector. So there is no more learning rate, but we have a full matrix, right? So instead of, say, if we have a network with million parameters, in order to actually do learning, we'll need million square parameters. It's huge. And each step now, instead of just making subtractions, takes much more. It takes, matrix vector multiplication. And the last thing is, it's oblivious to the network structures thing. I tried to tell you that, we need to be aware of, say, the architecture of a network, but we're still oblivious to it. So what we did is an algorithm called shampoo. This was a joke, but somehow it started, And the reason that it's called shampoo because this method is called preconditioning. So what do you do before you put a conditioner, a preconditioner? You put a shampoo, not on my head, but on. So it's a network. It's aware of the architecture. It's network aware. It operates on each dimension separately. And instead of getting into the math, notice the Google colors. I made them myself. I'm very proud of it. So if we have a network, so for instance, think of a network here as a three-dimensional cube. We're not going to precondition all of the cube at once. We're going to build these three hyperplanes that are going to precondition this network separately. Okay? What do we do with it? We go and look at the very largest, some of the largest problems. One of the largest problems that we have is called is language modeling. The goal here is to predict what's going to be the next word in natural text, given, say, a long history, a buffer of all the previous words. And this is not the largest data set. This is, I believe, available also outside Google. It's called the 1 billion words language modeling problem, or LM1B. And again, we need to predict the next word. We have 1 billion training examples, not huge, not extremely large, but fairly large. And we have a dictionary of about 100,000 words, meaning if an average person in English has about a vocabulary of about, say, 20,000 words. This is way more than, it's more than an educated journalist of the New York Times. Okay, and why do we use these language models? We use them everywhere. We use it in machine translation, in spelling corrections, in predicting in Google Suggest, which was developed in Israel, trying to complete your in auto completion. Typically, in order to train such large networks, we cannot go to many, to tens of layers. We have only 4 layers. These networks are complicated, are complex in terms of the number of parameters, but they're not that deep. And training time takes about 3 days. You say, 3 days doesn't sound much, right? But it's 3 days on tens of GPUs or hundreds of GPUs or tens of TPUs. So if we can cut the training time, we may be able to translate faster or better or complete faster or just perform larger tasks. So what you see here, and this will conclude my talk, is this is how the loss, how good the network gets. So think of this y-axis, without getting into the details, as a measurement of how good the network is, and this axis as time. This is number of training steps that we had to do, and look at the number of training steps. I don't know whether you can read. We easily get to 1 million training steps, and that's why it takes a few days to train. And what you see here is 4 different curves. This is how good a network gets. And think of the y-axis as, say, error. The lower it is, the better. And in black, you see a classical algorithm called the gradient-based technique, the one that has only scalar learning rates. In blue, this is one of the most popular algorithms for deep networks. It doesn't perform that well. In green, this is the previous incarnation of shampoo. And this is the new preconditioner. So this difference, which might look on the graph, pretty small, it actually means days. So instead of 3 days, it takes us now 1 day. So now instead of, say, 1 billion words, we can get, maybe in a week, to 10 billion words. And we can actually get even, we can start predicting also, proper noun, like the war in Bosnia-Herzegovina or something like it. There was one years ago. Okay. So we have a much faster reduction of training loss. We have better results and only modest increase in memory. So when you do these applications, it's not enough to think about time. These networks are very large. So if you increase the memory, you can't really do the training. Just about a word about implementation. So this is code that we wrote 3 people. I just disturbed them, but someone in a group did his PhD here in Israel, someone who did his PhD at Stanford, and myself. And we actually published the paper, and someone took the paper and implemented it on PyTorch. We have, of course, an internal implementation, and if you use TensorFlow, which is the programming language that we use to train these networks, it's going to be available as an optimizer, as a built-in optimizer. You can shampoo your network without really getting into the details. You just call the shampoo optimizer. It's going probably to be called something else. Okay, I'll stop here, and thank you so much for listening.